In Calculus 1, one of the applications of the derivative that you would have gone over would have been to start with a function that is a position function and understand that when you took the first derivative of that position function, you would get velocity. And then when you took the derivative of that velocity function, or the second derivative of the position function, you'd get acceleration. And so we're going to look at that same application here, but what we're going to start with is a vector function with a parameter t that gives us position. And then we can, as we learned in this chapter, we can then go ahead and take derivatives of the components of that vector to get velocity, and then the second derivative to get acceleration. And then, of course, remember that the distinction we make between velocity and speed is that velocity not only tells you how fast you're going, but it also gives you a direction. So then speed would just be literally just how fast you're going, so that's going to be the magnitude of your velocity vector. All right, so we'll also refer to this, by the way, as ds dt, and remember that the reason that we're going to do that is because ds dt is the rate of change of the distance traveled with respect to time, right? Because s is that arc length idea that we already talked about. So when we talk about speed, the magnitude of our velocity vector, that's the same as the derivative of arc length with respect to time. All right, so let's jump into an example here to kind of make these ideas a little more concrete. So it says that the position vector of an object is given by this vector function here. So we've got our x component and our y component. And they're saying that t is greater than or equal to 0. Okay, and so here it might be really nice to think of t as time, right? That makes sense because we're starting it at 0 and going up from there. And it says let the distance traveled be measured in centimeters and time be measured in seconds. Okay, so I guess I stated explicitly to think of it as time. All right, so we're going to first, in A, sketch the trajectory of the object. So, of course, we only have an I and a j component, so we know that we're just simply talking about something in the xy plane. And then from our work with parametrically defined vector functions, hopefully when you see the cosine as the x component and sine as the y component, that makes you think of a circle. So in fact, this will give us a circle. So let me just sketch it first, and then we'll make sure we're in agreement about that fact. This is not the best circle I've ever drawn, that's for sure, but get the idea here. All right, so fix that a little bit. All right, so this is what we're going to claim is the trajectory. Now let's make sure that this does in fact make some sense. So when I let t be 0, then actually I meant to make a table here. So when I let t be 0, my x is going to be the cosine of 0, right, which is 1. And then the sine of 0 is 0. So that puts me right here. All right, and then I can see if I put t equal to 1/4, for example, then I'm going to get the cosine of pi over 2, which is 0, and the sine of pi over 2, which is 1. And so if we continue to plug these things in, the cosine of 2 pi times a half would be the cosine of pi, which is -1. And you get the idea here. I won't go through all the details, but after a little bit, we convince ourselves that, yes, this should, in fact, form just a nice circle. And because we know that when we're taking when we're using the cosine of an angle and the sine of an angle to represent our x and y respectively, we started here, and then we're definitely, as t gets bigger, we're heading in this direction. So we can literally think of this kind of like a particle or something moving in the counterclockwise direction of this circle. All right, now in part B, it asks us to find the velocity of this object. So we know that the velocity vector is just the position vector's derivative, r prime of t. But we know how to take the derivative of this, right? So we have the chain rule, right? So the derivative of the inside of the cosine is the derivative of 2 pi t, which is just 2 pi, times the opposite of the sine of 2 pi t, and that's going to give us our I component, and then 2 pi times the cosine of 2 pi t. That's going to give us our j component. And so just to clean this up, negative 2 pi sine of 2 pi t and then 2 pi cosine 2 pi t. All right, now it asks us what the speed of the object is. Okay, so we know that that's just the magnitude then of this velocity vector that we just found. So that's going to be the square root of negative 2 pi sine 2 pi t squared plus 2 pi cosine 2 pi t squared. Now, this isn't for a specific value of t, right? They're asking us to figure out this speed as a function of t. So in here, we want to simplify as much as we can. So I see that if I square negative 2 pi, I get 4 pi squared sine squared 2 pi t, and then 4 pi squared cosine squared 2 pi t. But hopefully you're recognizing at this point that inside that square root we have our favorite trig identity, right? The Pythagorean identity. So if I factor a 4 pi squared out of all that, then I'm left with just sine squared plus cosine squared. And we know that that's always equal to 1. So the only thing left then is to take the square root of both of these, so that just gives us 2 pi, or approximately 6.28. And then this is a speed, right? So we can give this meaningful units, right? Remember that the position was measured in centimeters, the time was in seconds, so we can say that our speed here is 6.28 centimeters per second, and that speed doesn't change at all, right? Because we left this as a generic t disappeared. So what we're saying is that in this trajectory of this object here that's moving in this circle, the speed remains constant. It's always 6.28 centimeters per second. All right, now part D asks us to find the acceleration of the object, and again, that's as a vector, right? So we know that that is the derivative of velocity, right, which we found, the velocity we found in part B. So we go ahead and take the derivative of that. So that's going to be, I'll stick the same notation here, so the I and J notation. So I'm going to have negative 4 pi squared, and then it's going to be back to cosine 2 pi t. That's my I component. And then I'm going to have negative 4 pi squared sine 2 pi t, right? Because the derivative of cosine is negative sine. That's my j component. All right. Now in part E, it wants us to do something interesting here, and I do have a typo that we need to fix. So the typo is this, first off. It says sketch the vectors v over the magnitude of v, and what I meant to say was a, the acceleration over the magnitude of the acceleration. Wouldn't make sense to do the same thing twice. Okay, so those are the two things that we want. And we want to do that on the trajectory sketch for part A. So we want to do that for this trajectory right here. So let's go ahead and cut this out. And we'll add 2. Okay. Move that over here. We don't have to draw it twice. There we go. All right. And so it wants us to draw the velocity divided by its magnitude, the acceleration divided by its magnitude. Understand, though, that all we're doing by dividing by the magnitude is turning it into a unit vector. So this v over the magnitude of v, we're just going to understand this as a unit vector in the direction of v. And my only purpose in having us do this is to make sure that we can fit these sketches onto our picture, right? Because these are happening at 1, 1, -1, -1, right? So this is the unit vector in the direction of A. All right, so let's do that. And I say we should probably color code these. So I'm going to do my acceleration vector. That's going to be in red. And then my velocity vectors, we're going to do that in yellow. All right. So let's list out some values of t. And then at the same time, then let's go ahead and keep track of, for certain values of t, what do I get for the velocity and what do I get for the acceleration. And let's do the same values of t that we did on that previous page. So 0, 1/4, 1/2, 3/4. All right, so if I plug in 0 for v, and I'm going to, and rather than me clicking back to the other page over and over again, I'm going to have you just take my word on this, but I'm literally just plugging t into this formula here for the velocity, and then I'm plugging t into this formula right up here for the acceleration. Okay, so I'm not going to go through all the details. I don't want to take forever on this, but that's all we're doing. So what I get is the following. I get 0i plus 2 pi j when I plug 0 in for v, and I get -4 pi squared plus 0j for the acceleration. All right, remember we're going to do velocity in yellow, we're going to do acceleration in red. So this velocity one, what I'm going to do is I'm going to have the vector take off from the point where t equals 0. So that would be right here. Now, if I have 0 for the x component, that means I have no left or right movement, and all my movement is in the y direction. So that means I have a vector pointing up like this, right? And because I'm plotting the unit vector, it's just going to go up to a height of 1. Now my acceleration from that same point is a negative x value and a 0y. So no movement in the y, but negative movement in the x direction. So that does that. All right, now let's do a couple more. So we've got -2 pi I plus 0j. If I plug in 1/4, and I have 0i minus 4 pi squared j for acceleration. So what does that do? Well, the velocity would be negative in the x component, 0 in the y. So that means it's going to do this. And then the acceleration, 0 in the x, negative in the y, means it goes down here. All right, and at this point, you could probably guess at what's going to happen with the others. I'll just quickly sketch them out here. 0i minus 2 pi j for the velocity, 4 pi squared for the x, 0 for the y, for the acceleration, and then we'll also do the 3/4 here. 2 pi I plus 0j, 0I plus 4 pi squared j. And so that gives me a velocity vector here that looks like that, a velocity vector here that looks like that, and then my acceleration vector is pointing in toward the middle. So what you have is when you have circular motion, with that circular motion, your velocity vectors or your derivative vectors are always going to be tangent to the path of movement, right? So it's always tangent here. And we know that that's the case just generally because of what a derivative vector means. So the velocity is in this direction. However, acceleration is toward the center, right? So think of this like it's like the orbit of a planet around some star. Then what you have is the velocity is going this way. So what does the object want to do? It wants to shoot off this way. It wants to not be in orbit, but of course there's a massive star in the middle that's holding it there, which causes an acceleration inward, which is what gives us this orbital path. All right, so we're going to apply this idea to a slightly different situation here. So it says that a baseball is hit from 3 feet above home plate with an initial velocity in feet per second of 80I plus 80J. They're asking us to neglect all forces acting on the ball except gravity, which they're giving us is 32 feet per second squared. All right, now gravity, right, like they said, is a force. Force is, remember, mass times acceleration. So when they're giving you information about acceleration, they're giving you, or excuse me, giving you information about force, they're really giving you information about acceleration. So the idea here is if gravity is the only thing acting, then I can start by writing out A of t and saying that A of t is the vector 0, right? There's no acceleration in the x direction. And then, of course, because it's gravity, then we're talking about going downward. So we'll call this negative 32, right? For negative 32 feet per second squared. All right. It asks us to find the velocity vector, but that's okay because we know then that the velocity would have to be the antiderivative of acceleration, right? If acceleration is the derivative of velocity, then velocity is the antiderivative of acceleration. So what happens here is that we can take the antiderivative of 0, right, which is a constant of some sort, I suppose. And then the antiderivative of negative 32, which would be negative 32t. And then that would be plus some other constant d, we'll call it that. Okay, so we've taken the antiderivative of both of those things. Now the reason that they gave us this information about initial velocity is so that we can now go back to this equation that we formed and figure out what these constants actually are. So when I know, for example, at v of 0, well, according to this formula, it's c comma d. But then I also know from up here that that's equal to 80 comma 80. So what that tells me is that both those constants c and d are equal to 80. So that means that my velocity vector has to be 80 and then negative 32 plus 80. All right. So then in part B, it wants us to find the position vector of the ball at time t. Okay, well, we know that position would have to be the antiderivative of velocity. right? So we have r of t would have to then be, well, let's take the antiderivative of 80, so that'd be 80t plus, and hopefully you don't mind me just using the same constant symbol again, we'll say plus c. All right, and then here, remember what we got to do is we got to take negative 32 t squared over 2 plus 80t plus some constant, we'll call it d. All right. So do we have any initial information that tells us what c and d ought to be here? Well, they did say a baseball is hit 3 feet above home plate. So from 3 feet above home plate, that means that when the time is 0, the instant the ball is hit, right, we have gone 0 in the horizontal, but we have gone, or we are starting up 3 in the vertical. So there's our initial position, and so then we can use that just like we used the initial velocity in this other problem. So we know that r of 0 on the one hand is equal to c d once again, which is equal to 0, 3, based on this information from above. So c equals 0, d equals 3, so our position vector would be just 80t all by itself, and then here negative 16t squared plus 80t plus 3. So that's got to be the position vector for my baseball. All right, so now what we have is that it says show that the path of the ball is a segment of a parabola and then make a sketch. Okay, so how do we do that? How do we show that it's the segment of a parabola? So this would go back to work that you might have done, especially maybe back in a trigonometry class. You would have done a decent amount of this, is where you write a parameterized equation in rectangular coordinates once again. So never lose sight of the fact that when we say that we have this position vector that's equal to this, what we're really saying is x equals 80t and y is equal to negative 16t squared plus 80t plus 3. And so what you can do is take this x equation and say, okay, well that means t is equal to x over 80, and then you can plug that in anywhere you see a t in the y. So negative 16 x over 80 squared plus 80 times x over 80 plus 3. And so that means that the y simplifies down to, we can do a little bit of simplifying here and get negative x squared over 400 plus x plus 3. And so one thing that we can always do is we can set y equal to 0 and find the x-intercepts. And I'm going to not do all the detail work there. Quadratic formula works great. Put in your calculator, doesn't matter. We get about 402 as the x. And so what that means here is that if I wanted to make just a very quick and rough sketch of this, we're starting by hitting the ball, right, 3 feet above the ground. So here's y, here's x. And then we're way, way out here at about 400, just past it. That's where we're going to cross again, right? So then, of course, between there, we are forming a parabola. And we know that because we have the classic ax squared plus bx plus c form that we're used to. All right. So the last question here is it asks a nice practical question. If you're a baseball fan, does the ball clear a 20-foot fence that happens to be 380 feet from home plate, right? So in other words, if I go and I draw a fence right here at 20 feet high and it's supposed to be at 380, right? Does it look like that, or does the fence go a little higher and does the ball, bounce off of it? So that's the question for us, but of course we can answer it pretty easily, right? Because all we have to do then is take that work we just did, the y equals, and go ahead and plug in 380, which is the x value, and see what happens. And when we do that, we get 22 feet. So since the fence is only 20 feet high, we do have the ball clearing the fence by 2 feet in this case. All right, so we're going to do one more example that has some multiple parts to it. And so to begin this discussion, what we're going to be looking at here is when we have a projectile that is, fired, thrown, launched, whatever, with a certain angle and a certain initial velocity, how can we set up our equations for that? So the thing that I would remind you of here is that if you launch a projectile at a particular angle alpha and with a speed of v naught, right? So we'll say angle equals alpha, speed equals this v0, not a vector, just this quantity v0. Then what we know is that we can turn that information into a vector, turning it into its x and its y components by just taking the magnitude or the speed times the cosine of the angle for the x and times the sine of the angle for our y. So that's what we're building this off of. So if this is going to give me, this is my initial velocity here, then what we can define is the parametric equations for the position of this projectile if you've got an initial velocity of v0 and you have an angle of elevation of alpha, is going to be this, right? It's going to be v0 cosine alpha times t, and then v0 sine alpha times t minus 1/2 gt squared, okay? Now this is just simply formalizing what we did on this previous page, right? So all we're saying is, remember what did we have here? We had this negative 32 t squared. What was the negative 32? That was the acceleration due to gravity. We chopped it in half. So it was really 1/2 times the gravity constant times t squared plus the initial velocity times t plus a constant here, right? Now, so that's what we said. We're just formalizing that here. So this 1/2 gt squared, that's that negative 16 t squared from the previous page. That's all we're saying, okay? So we're just formalizing this, and this one is fired from the ground, and so that's why we don't have the +3 here, okay? But besides that, that's all that we did, but we're just kind of writing it as a formula. All right, so equipped with that, now let's take a look at this example. It says a golf ball is driven down a horizontal fairway with an initial speed of 55 meters per second at an initial angle of 25 degrees from a tee with negligible height. So just imagine the ball's pretty much starting from the ground. So we're going to neglect all forces except gravity and assume that the ball's trajectory lies in a plane. What I mean by lies in a plane is that the golf shot does not look like most of my golf shots, which is there's no slice to it, there's no hook, so you hit it and you can draw a plane that goes straight off from where you're shooting at, that cuts through, and the ball stays in that plane. It doesn't veer left or right from there. So it says, how far does the ball travel horizontally and when does it land? All right, so using these formulas, we can write out what the x and y components would have to be. So my x is going to be the initial velocity, 55, times the cosine of the angle, all that, times t. And the y is similarly going to be 55 times the sine of my angle, times t. But then we have to say minus 1/2, and then here we have 9.8 meters per second squared because we're talking in meters this time. So it'll be minus 9.8 t squared. All right, now it asks us how far does the ball travel horizontally and when does it land? Okay, so in order to figure out how far it travels horizontally, we need to know what is the t value when it lands, right? Okay, so we actually need to answer the second question first. When does it land? Or in other words, when is the y value going to be equal to 0? So we can start by setting that. So it'll be 55 sine of 25 degrees times t minus, we'll go ahead and fix that up, 4.9 t squared, make it a little easier. All right, now I have a t in both terms, so we can pull that out. So we have 55 sine of 25 degrees minus 4.9t. So of course t equals 0 is a solution, but that's pretty boring, so we'll just ignore that and move on. So we'll set this equal to 0. All right, solve for that and an approximation. So when I do divide both sides by 4.9, what I get is that t is approximately 4.74 seconds. All right, so that's the when does it land, right? It lands after 4.74 seconds. Right? If you were golfers, they kind of think, does that make sense? And yeah, if you hit a decent shot, should hang up there a little while. And then, of course, how far does the ball travel? Well, that's where we can go to our x value and say, well, let's go ahead and plug in that, and what we get is x is approximately 236.3 meters. Okay. So, not such a great shot if you're a pro, but I'll take 236 meters any day for a tee off. So not too bad here, at least as far as an amateur is concerned. All right, but continuing on with the same thing, it asks us what's the maximum height of the ball. Okay. Well, if we want to know the maximum height of the ball, that should remind us again of Calc 1, where we start talking about derivatives, right? And setting derivatives equal to 0 to find the maximum or the minimum. But in this case, right, we're looking for the maximum height of the ball, right? So it's probably, the x probably isn't too important here. Let's look for the derivative of y. So we'll find y prime. And of course, y prime just is 55 times the sine, 25 degrees times t, and then minus 9.8t. Oh, excuse me, I don't know why I said t here. That shouldn't be there. So 55 sine of 25 degrees because we took the derivative of t and it became 1. And then here, from the previous page, right, taking the derivative of this, 2 times 4.9 is 9.8. All right, and we set that, of course, equal to 0, right, to find when it's at its maximum. So 9.8t is equal to 55 sine of 25 degrees divided by 9.8. So t is approximately equal to 2.37 seconds. Okay, now that is when we reach the maximum height, right? But that doesn't tell us what the maximum height actually is. So for that, remember we have to plug that back into the original y. So I'd go back 55 sine of 25 degrees times 2.37 minus 4.9, right? This is going back into y, times 2.37 squared. What I get there is about 27.57 meters. Okay? That's how high the ball got when it was at its very peak from the shot. And then one other kind of interesting question here. It says, at what angles should the ball be hit to reach a green that is 300 meters from the tee? Okay. At what angles, and notice there's a plural there, that's kind of interesting, right? But what angles should the ball be hit? So if I know that my green is 300 meters away, that means I know my x, right? So going back to the last page, going back to there's the last page. Then I know that what I'm doing is I'm setting this one equal to 300 and seeing what the t ought to be, right? So let's do that as a starting place. So we take 300 equal to 55 times the cosine. Okay, but here's the deal. This time I don't know what the angle is, right? So they're starting over. They're saying, okay, what angle do you hit so that the x component is 300? Right? I don't know alpha and I don't know t. All right? So that's what I want to try to solve. Two unknowns in a single equation is problematic, so we need another equation. Luckily, though, we also know that we're not just shooting for being out there 300 meters. We're also shooting for our horizontal component to be 0 at that point, right? So we know we're going to set 0 equal to 55 sine of alpha times t minus 4.9 t squared. All right, now here we can get an idea of the relationship between alpha and t. If we factor out a t here, we get 55 sine of alpha minus 4.9t. Set that one equal to 0. 55 sine of alpha minus 4.9t equals 0. All right, and what we find is that my t is equal to 55 sine of alpha divided by 4.9. Now, that just gives the relationship between t and alpha, but what it does allow me to do then is take this and then go and plug it in where I see a t in the x equation. So we'll go ahead and do that. We've got 300 equals 55 cosine of alpha, and then t is going to be 55 sine of alpha divided by 4.9. All right. Now if I multiply by 4.9 on both sides, then I end up with 1470. And then if I multiply 55 times 55, I get 3025 cosine alpha sine alpha. All right, now here this might, I suppose, be a little bit of a stretch for us to remember, but if you've got two different a cosine times a sine, remember this is the double angle formula for sine. So what we can do here is multiply both sides by 2 over 3025. The reason I'm multiplying by 2 over 3025 is because remember that that the double angle formula for sine has to have a 2 in front. So what I have over here on the left side is 2940 over 3025, and that's equal to 2 cosine alpha sine alpha. But that, based on the double angle formula for sine, is the sine of 2 alpha. All right. Now at this point, we know that if we want to solve for sine, we've got to use the sine inverse. So we'll go ahead and say 2 alpha is the inverse sine of that number from the left, which means alpha is equal to 1/2 times the sine inverse of that. And when you crank all that out in your calculator, what you get, especially if you put yourself in degree mode, is 38.20 degrees. Okay, so that might seem reasonable. I can get there if I hit at an angle of 38.20 degrees. Okay, but the other thing I want to remind us of is remember whenever you solve for sine, I'm going to have to put this over here, put it in a different color. Whenever you solve for sine, what we have to remember is that there are always 2 places on the unit circle where the sine will take on a particular value. So if, say, this angle here is one of your solutions, then remember sine is the y value on the unit circle. So this angle over here would also be a solution. And that angle you get by taking 180 degrees minus your first angle. So at this point right here, what we also wanted to do would have been to say 2 alpha is equal to 180 degrees minus the sine inverse of 2940 over 3025. So that means that alpha is equal to 1/2 times 180 degrees minus the sine inverse of all that. So alpha is approximately, when you crank all that out, 51.81 degrees. So this is kind of an interesting solution. You get 2 different angles, okay? So what does that mean? What it means is that we can, either hit kind of more of a line drive, right, to get there, or we can hit more of an arc to get there. You got those 2 different possibilities. Now I would say this is the better solution, right? Know anything about golf? You hit those line drives, it tends to skip right off the green. It's those big higher shots that allow the ball to kind of settle down a lot more nicely and just plop right on the green and stay put. So this is the angle I would choose, but both are technically solutions to this problem.